let's see. So the title of this talk, I'm hoping, is not too much of an oxymoron. How many people have any experience with Haskell? OK, pretty good, maybe half people. How many people have no idea anything about Haskell? OK, it's a programming language. So sort of the attempt of this talk today is to sort of describe some rather simple features of Haskell. Haskell, maybe even if you don't know much about it, there's a decent chance that you have sort of an impression that it's a complicated language. It has almost this kind of mystique about it. And I'll admit that's kind of what encouraged me to learn it for the first time back in 2010 or 2011. I didn't know anything about functional programming. A friend of mine was getting his PhD and was doing some Haskell stuff, and he's talking to me about pure, lazy functional programming, and I'm like, those words don't mean anything. And so I read a Wikipedia article about it, and to me, literally, the paragraph made absolutely no sense. And that kind of frustrated me to no end. I had a degree in computer science. I thought I knew at least a few things. And there's this whole branch of programming languages that I knew nothing about. And so I started learning Haskell just sort of out of spite for not understanding it. But it definitely had this reputation of kind of being this difficult to understand thing. And the truth is, a lot of that is well-deserved, both for kind of real reasons and some kind of cultural reasons, which we probably won't talk too much about. But Haskell's really expressive. You can do a lot with it. You can sort of ensure that parts of your program definitely do or definitely don't do certain things. And there's a lot of kind of extensibility where complexity comes in. But I'm going to try and kind of show you just using absolute basic stuff you would learn in your first week of learning Haskell, how much power is there, and hopefully kind of tempt you to learn Haskell and sort of be OK just learning a little bit and feeling like there's power there. I think a lot of us who have kind of done some programming before and have maybe gotten pretty comfortable with a language like, say, Ruby or Python, it can be difficult to kind of learn something new and accept that there are some things that you don't understand yet. Once you've kind of mastered something, I think sometimes there's a feeling of I don't really feel comfortable until I sort of understand how this whole thing works. And sometimes when you learn new languages, you kind of have to put that to the side for a second and say, OK, there's some more complicated stuff that I don't understand. But I sort of accept that I can do some really cool things with just this little bit of knowledge that I have. And hopefully I'll kind of motivate you there. This is definitely not an introduction to Haskell. That doesn't mean that it won't be introductory material, but this is not at all kind of an overview of Haskell. It's sort of seen through a very specific lens of using types in hopefully some cool ways, but it's not intended to sort of be an overview. So if you leave today saying I didn't learn Haskell, that's OK. I'm not teaching you Haskell. This is going to be really casual, so if you have questions, feel free to interrupt me. Depending on the question, I might ask you to ask it again at the end if it's kind of better suited there, but definitely don't hesitate to ask questions. OK, so we're going to do just a little bit of a history of Haskell, at least kind of how it serves this talk anyway. So Haskell is kind of a relatively rare designed by committee that turned out actually, I think, in a good way thing. So this is some of the members of the Haskell committee, which I believe first started in either 1989 or 91. And they were basically a group of functional programming researchers that saw some ideas from a language called Miranda and wanted to kind of expand on that and come up with a new language specifically for research. And that kind of informs a lot of the sort of extensibility part of Haskell, where admittedly a lot of the complexity comes. So sort of a overview of the type system. Haskell has a strong static type system. So there's kind of two halves to that. There's the strong half and the static typing half. Strong is to be contrasted with weak. So a weak type system basically means that the programming language is sort of going to allow you to sort of coerce types together just as you want. So in JavaScript, for example, I can add a number to a string, and at no point during compile time or even at runtime does JavaScript say, hey, this is a number, this is a string, they can't be added together. It just sort of does that for you. So that'd be an example of a weak type system. Strong type system sort of says, hey, these are two different things. You have to sort of cast one of them if you want to be able to do that. The other half of that is sort of when this type sort of matching up happens. Does it happen when you compile the program and sort of prevent or allow the program to even compile based on whether the types sort of fit together or don't fit together? Or does it happen at runtime? So Ruby, Python, you sort of run your program and you can try and do all sorts of stuff that makes no sense. The program runs, and then if that code happens to be executed, it throws an exception and says, hey, you can't add a number to a string. You have to sort of cast one, or you found a bug. So that's a dynamically typed programming language. Statically typed programming languages, all of that sort of type checking happens at compile time. So once you've compiled your program and it successfully compiles, it means that you're completely free of type errors. There will not be runtime errors in Haskell programs that are due to types being mismatched. All right, so there's been sort of an evolution of Haskell, and part of it being sort of designed by a committee and actually being designed sort of separately from an implementation. So Haskell has a specification. There's different compilers, GHC being kind of the most popular one, but there's a specification that's kind of divorced from that, which is kind of cool because it means that compiler bugs don't become part of the standard. Compiler bugs are that. They're just bugs. They don't sort of become, oh, this is how things were because there was a bug back in 1994 and we didn't write anything down. So there's actually a standard, which is kind of cool. The standard has evolved over time. The most recent one is Haskell 2010, and there's a committee that's working on Haskell 2020 right now. And Haskell kind of has phases of compilation. This is going to make a little bit more sense in a second, but you sort of write your Haskell code, and then it compiles down to a simpler language called core, which then gets compiled down to something called STG. This is with the GHC compiler. And that gets compiled down to something called C++, and then you have different backends that you can actually use to compile your code down to machine code, be that LLVM, or actually you can compile to C and then use something like GCC to compile to machine code. But it's not important that you kind of understand this whole pipeline, but the sort of takeaway here is that we're starting with this pretty high-level language Haskell, and then we're compiling it down to a simpler core that in some ways might be more verbose, like we have to explicitly annotate all of our types in core. There's no type inference. A lot of the kind of higher level complex type theory stuff you can do in Haskell is all kind of done and compiled away by the time we get to core. And this is cool for a couple of reasons. One, it means that we kind of can experiment with new ideas for extensions in Haskell. And if we can sort of create a new extension to the language that can be represented by core, we sort of have an idea like, okay, this is not some absolutely crazy new thing. This is representable with ideas that we already have. The other kind of takeaway from this, though, is that this relatively simple, core is a relatively simple functional programming language, has enough power to represent all of these other complex ideas. And so just learning kind of the bare minimum parts of Haskell actually gives you a tremendous amount of power. And we'll see why that's useful. Because Haskell has all of these extensions, well, G8C in particular, and there's a few of them. I'll give you another second or two to memorize all of these. So these are extensions to the language that you can sort of turn on for, at like an individual file level, and the extension only applies to that file or for your whole project. And some of them, admittedly, are really complicated. And if you read blog posts about Haskell that, seem really complicated, there's a non-trivial chance they're using some of these extensions. That doesn't necessarily mean they're bad, but it can kind of give you this false impression that in order to learn Haskell, you have to learn all of these really complex things. Haskell is a language that you can spend 30 years using and never sort of know everything. But that's okay, because the core is actually really powerful. So I sort of ask you to, be okay not understanding what all of these things mean. I've done Haskell for 8 years, and if I'm lucky, I understand maybe a third of these, and that's okay. I've written Haskell professionally and only understand a third of these. That's totally okay. It means that I have a lot of cool things that I can still learn, but there's a ton of power even if you don't understand all of this. Okay, so let's get into some really simple types in Haskell. So the way we're going to read this, there's like a data type literal on the left, and then we have this double colon. The double colon basically just means this thing has this type. So 5 has the type integer, the string foo is a string, true is a bool, and 1, 2, 3 is a list of integers. So this is basically us just sort of introducing the syntax for the Haskell type system, and sort of types that you would expect are just as simple in Haskell as you'd expect them to be. And so there's kind of built-in batteries included types the way you'd expect. But where a lot of the power comes is creating our own types. And a lot of the kind of simple domain-specific power we're going to talk about here is from creating your own types. And there's a few different ways of doing that. There's 3 different ways, to be precise. And they all have names that, just pretend these are proper nouns. Don't try and glean anything from the words used here. Like category, type, kind, just they chose a particular word, that's the word they chose. Don't try and glean too much from it. You just have to sort of accept that data means this thing, and yes, data is creating a new type as well, but there's a separate thing called new type. There's also something called class and called kind and called type. It's confusing, but you'll get the hang of it. But we're lucky, we're only going to look at 2 of these today, because this third one kind of isn't important for today. So just forget about it. Forget about type. We're only going to look at data and new type. We're still going to create new types and new type, but we're going to ignore this third one. So let's look at the first one called data for a second. If you want to get fancy, this allows us to create something called an algebraic data type. But for now, we can sort of think of data as allowing us to sort of create data types from sort of either alternatives or from the addition of multiple types. So in the case of Boolean, this is literally how Boolean is defined in Haskell. So bool is either true or false. These don't mean anything. The compiler doesn't know anything about TRUE. This is just sort of almost like an atom in some other languages, or like a keyword in Ruby. It's sort of just a token. It doesn't even necessarily equal itself unless you define it to equal itself. So a Boolean is something that's either true or false. These are just sort of tokens that we've created. We could have easily written these in Spanish if we wanted to, and it would have been totally fine. Other programmers might not have understood it, but we could have done what we want. So we can create a data type to represent stoplight colors, so green, yellow, or red. So that was kind of alternatives, right? So if you have an instance of stoplight, it's either green, or it's yellow, or it's red. Just the same way if you have a number, it's either 4 or it's 2. We can also create compound data types. So like a struct in C, or a record in some other languages, or like an object in object-oriented languages. So we can create a coordinate type, which is going to have 2 integers. And we can also create a tuple. Now we're doing something a little bit different here. Before, when we defined tuple, we said that it has 2 integers in it, right? So this coordinate type only works for integers. We could also create a tuple type, and this says it has sort of 2 fields, A and B, but notice how we're using lowercase letters here. Basically, this just means that a tuple can contain any 2 types. So when I create a tuple, I'm going to sort of like instantiate those 2 types. So I could have like a tuple of float and bool, or a tuple of cat and dog. And once I sort of assign those types, I can only use a tuple that has the correct sort of filled in types in a place. So if a piece of code requests a tuple of 2 Booleans, I can't pass in a tuple of cat and dog. But this basically allows us to sort of create data types that don't care what the sort of inner contents are. And that becomes useful for things like sort of collection type data structures. So here we're going to define a binary tree. We're not saying what it's a tree of. It could be a tree of Booleans. It could be a tree of oranges. Not important that you necessarily understand how this works. There's some cool recursion in how this is defined. So we're saying a binary tree is either a leaf node that has whatever the actual element is, so our A, let's say it's oranges in this case, or it's a branch that points to 2 other trees. So we can actually use tree itself in the definition. That tree should be binary tree. There's a little typo there. So we can actually use binary tree in the sort of creation of a binary tree, which is kind of cool. Again, not super important that you understand this, but this allows for some really cool, concise things that allow you to sort of define these types in a really elegant way. We can create things that look a lot closer to the type of programming that most of us do. Most of us are not kind of creating data structures in our day jobs where we're dealing with particular business domains, right? So we can create a person, maybe that has a string and an integer. But that's maybe a little confusing. We don't know what the string means and what the integer means. And so there's just kind of like a syntactical sugar syntax that allows us to say, we're going to give those fields names. So a person has a name, which is a string, and they have an age, which is an integer. And so instead of kind of dealing with things sort of like a positional way, like the first field means name, the second field means age, we can just give them field names. Again, if you've used object-oriented languages or languages like C that have structs, this is all pretty familiar. Any questions about that stuff so far? Cool. All right. We're going to move on to the second one. This is kind of the meat of the talk. What's cool is that this one's actually way simpler. So if you've understood so far, it's only going to get easier. And this is, I think, one of, if not the most underrated feature of Haskell. This is a super simple feature, and in sort of day-to-day sort of encoding business logic, which is most of what we do in software, has a lot of really cool benefits. OK, so new type is going to create a new type. As I said before, don't take too much from that meaning because all of these things are kind of creating new types. But basically what new type does is it allows you to take an existing type, give it a new name, but in a way that your type that you've just created is actually different than the underlying type, right? So I'm going to create a type called name. This is going to represent, a human name. Its sort of underlying representation is a string. I can derive properties from strings. So a lot of kind of modularity and code reuse in Haskell comes from something very similar to interfaces in other languages. So string implements all of these useful interfaces. In Haskell, we call them classes, but in other languages, you're probably used to them being called interfaces. And so there's all this like amazing functionality that comes from something being a string. It can be printed. Two strings can be compared with each other. Strings can be serialized over the wire. Strings can be stripped of white space. All of these kind of cool things that we can do with strings. And so this allows us to sort of create a type which has as many of the properties as a string as we want. So we get to actually be really explicit about which properties of string we want and which maybe we don't want for maybe some safety or correctness reason. And this is like one line of code. And what's cool, though, is that I can't ever mix up a name and a string. And so if my function requires that you pass in a name instead of a string, you have to pass in a name and not a string. In most programming languages, like let's say Ruby, Python, if we had a person's name, we would just use the built-in string type. We would use the built-in number or integer type for their age. And it kind of means that at any point in our program, if we just have a string or a number, let's say we're debugging something and somewhere in the call stack we see there's a number. We don't really know what that number means. Yeah, it's a number, but a number could mean dollars. A number could mean a person's age. A number could mean the street address of this location. And in other languages, we're certainly capable of kind of creating types that represent those specific things, but there's typically a lot of downsides to doing so, either boilerplate or complexity trade-offs. In Haskell, it makes it really easy for us to sort of give new names and use all of the functionality, the internal representation, as kind of an added bonus. At runtime, all of this goes away, and we only pay the runtime overhead for a string. So we just get that for free. It's the exact same performance as if we used a string, because all of this safety and benefit that we get from it happens before you run the program at compile time. Once that's done, we can just pretend it's actually a string. So we get all the same performance of using the same underlying data structure that we might have kind of reached for in another language. Is this making sense? Cool. So just to kind of drive home a few of these properties. So we created this new type called name. Its underlying representation is a string. And so I'm sort of asking, is read the string equal to name read? What's going to happen? Is it going to say false? It won't compile. Yeah. So that's pretty cool, right? So how many of you have ever called a function and it has 5 arguments and they're all strings or integers, and yeah, pretty much every function, and you've flipped the arguments in the wrong order on one of them? I've done that a lot. This helps prevent that problem massively. We'll see an example of that. But it also means if I ever sort of have sort of a handle on something that could traditionally just be represented with a string or an integer, in a really cheap way, I can give it a lot more meaning, which is great for refactoring, but it's also great for understanding what we think a function is going to do. We'll see an example of that in a second as well. OK, so far we've only seen types of sort of just values. I'm going to introduce types for functions. So the syntax looks very simple. Let's say we've introduced a function called multiply by 2. It's going to take an integer and multiply it by 2. It's a very simple function. And so the type of this function is it takes integers and it returns integers. And however many parameters your function has, that's how many kind of type arrows you have. And then the very last thing on the right is the return value of the function. OK, and then I'm going to introduce it with just a little bit of indentation, just the way the slides are written. This is kind of the format that I use in the rest of the slides. So this is the same thing. It's kind of strangely formatted, but we're saying multiply by 2 has type integer to integer. So it takes a number, multiplies it by 2, and returns a new number. OK, so let's create some new types. Let's say that we're creating a web application, and we really care about security, so we're not going to store our users' passwords in plain text in the database. And so we're going to hash the passwords before we store them in the database. We want to make sure that we do that. So we want to make sure, one, that we hash the password before it goes in the database. We want to make sure we hash it how many times? Just once, right? Because when we compare it the next time, if we've written the code correctly, we're going to hash it once, compare it with what's in the database. And so in just a couple lines of code, we're going to create some sort of domain-specific types for ourselves. So we have a plain text password type and a hashed password type. They're both backed by string, which is the same type we would use if we were doing this in Ruby or Python. But now the type system kind of lets us know, has this password been hashed yet? And so our function that says like store password in database can demand that it only takes a hashed password. And so if you have called that function, you have necessarily created a hashed password type, right? All right, so we're getting some safety here. And in order to allow the user to create a hashed password type, or our fellow developer, we're going to create a function called hash password. It has type, it takes a plain text password, and then it returns a hashed password. We can kind of ignore this IO monad bit here for now. So when we call the function, we say hash password. We're going to call something called a constructor. So this is how we actually create a plain text password from a string. And now we get our hashed password, and we can provide it to the store password in database function. So we can see here that given a string, we can create a plain text password type. But this kind of begs the question, or raises the question, why can't we just, maybe our lazy developer just creates a hashed password directly from a plain text string? We don't want people to be able to do that, right? Because now we're kind of relying on like culture and like sort of oral, encouragement as a way to say, oh, use the function this way. And it turns out that there is a way of solving this with modules. A lot of this is actually very similar to object-oriented programming, or at least the promise of object-oriented programming. So this is a real Haskell module. This compiles and is pretty close to what you would actually write if you were doing this. And let's see if the laser pointer shows up now. at the very top of our module, so we're going to create a new module. It's called password. And then we're defining the sort of names that we export in our module. So anything that we don't explicitly export here is going to be hidden. Not like hidden in sort of interpreted dynamically typed languages where if you really want to sneak in and get at it, you can. Like, no, it's actually hidden. So we're going to create the same types that we did before, plain text password and hashed password. And when we export plain text password, this is just sort of the syntax for saying we're also going to give you a way to create a plain text password just directly from a string. So the underlying representation of plain text password is string. And so if you want to create plain text password directly from a string, we're going to give you the constructor. Somewhat confusingly, it's also called plain text password. These are actually sort of like different namespaces that are here. And so it can be a little bit confusing because oftentimes for sort of consistency, we'll use the same name in both places. But the one on the left is the name of the type. The one on the right is sort of the name that you call when you're creating this thing from a string. Don't worry if that doesn't make a ton of sense. But with hashed password, we're only exporting the type hashed password. Basically what that means is that other modules, other programmers can use this type, but they can't just create them out of thin air from a string. And then we're also exporting a function which takes a plain text password and returns a hashed password. And so because we haven't exported the sort of like internal representation of hashed password, the only way that you can sort of have one of these types in hand is necessarily that you call this hash password function. So that's pretty cool. It allows us to have other functions in our code that take a hashed password as input, and we can be guaranteed that the plain text password has been hashed exactly once and haven't done anything else to it. We can't hash it and then forget if we've hashed it and then hash the hashed one again and now it's been hashed twice or 3 times or 0 times. It is hashed exactly once. And we've done this in whatever this is, 10 lines of code. So we're really encouraged to kind of program at this level of specificity with our types. It only takes 2 lines of code to create one of these new domain-specific types. If we want, we get as much of the functionality from the underlying representation as we want. So we're not like re-implementing all of the functions for string. We get to sort of reuse and borrow as much of that as we want. And so in sort of typical idiomatic Haskell, you'll often see hundreds of these types that represent all sorts of different things in your domain. And it makes it really evident when you're looking at functions, even if they have no documentation, you can sort of suss out what you expect that they're going to do, and it makes refactoring really nice and easy. OK, so we've seen that with this module, we can create a plain text password from a string. That's good because when we read the string off of an HTTP request, it's just going to be a string. We need to sort of be able to wrap it in a plain text password. We can hash a password, and then we can also use the type in our own functions to require that something's been hashed. But the only way that we allow people from our module to hash passwords is calling this one function that we've exported. Seems like people are kind of understanding, so we'll go through this next example quickly. But don't hesitate to interrupt me with questions. But it turns out that this kind of pattern is pretty common. We see this for sanitizing input, for sanitizing output before generating HTML, for validating things, for making sure that certain operations have been done. So you can imagine doing something with different fields that you accept from forms. So maybe you strip white space from all of your form input. It could be something that doesn't even necessarily have a security concern. You're just sort of, prettifying the input that someone has entered a form. If they have trailing new line on it, you're going to get rid of it. And in order to do that, you kind of represent it with two different types. You have the type that you read off the wire from the HTTP request. So in this case, we're going to do an example of validating an email address. So we have our input email, and then we have our validated email type. And if some part of our program takes a validated email as the input to the function, we know that the only way that we can sort of create a validated email is by calling this function. So this is very similar to the last example. I mean, it's basically identical. We have an input email and a validated email. They're both built on the underlying string type. We export the ability to create an input email from a string, but not a validated email. And then we export a function called validate email. One place this is different, though, is that an email might not be valid. And so instead of our return type being validated email, it's maybe validated email. Typically, Haskell does not have a notion of like null or undefined in the type system. So maybe sort of allows you to say that this function might not return a validated email. So it's going to try to return a validated email type, but if the email is not valid, it's going to return nothing. And so if you pass in an invalid email, you will not be sort of allowed to create a validated email. And what's kind of cool is that because we've wrapped it in this maybe type, the sort of caller of this function is sort of forced to deal with the failure case as well. Or at least they're encouraged to. There's a couple of escape hatches there. OK, so basically same thing. We can create an input email type. We can validate an email, and we can require a validated email type. So let's talk a little bit about how this helps with refactoring. I think we're going to touch a little bit on sort of code sort of inherent documentation as well. OK, who knows what this function does? It's pretty obvious, right?
Triple function?
Could be.
Take function returns a function that would return a function.
Yes, actually, in Haskell, that would be correct. But it's just taking a bunch of numbers. We have no idea what this is doing, right? OK, so let's take a function that has the same shape. We're just going to give more specific names to these numbers. What does this function do? Any guesses? Yeah. So we don't even have the name of the function, let alone like a doc string. But just from the types, in like 3 seconds, we've been able to guess what this function does. Now, this is not at all to say that you shouldn't give your functions good names or that you shouldn't write documentation, but this really helps a lot in sort of conveying the intention of your functions to other developers. And because it's so easy to sort of create these specialized types, you're really encouraged to do so in Haskell. OK, so let's say that we had represented it just with integers. And if we were writing idiomatic Python or Ruby, that's what we would have done. Like the function, well, I wouldn't have even said what the types were, because neither of those languages have sort of a type system that you write out the types. But you would have just expected the function takes 3 numbers and returns a number. And like maybe if you look at the code based on the variable names in the definition, you can tell which one is the principal, which one is the interest rate, and which one is the number of years. And let's say that, this is kind of an example we talked about before, but let's say that we're doing a refactor, and for some reason we're realizing that this function would be so much nicer if we swap the order of the arguments. So it's the same function, but instead of passing integer first and integer second, you pass, that's kind of confusing, right? So we're swapping the order of the arguments. And even in Haskell, if we did this, if we redefined the function to swap the order of the arguments, all of the code that called this function would still compile. So even in Haskell that has this kind of amazing type system, we can make mistakes like that if we don't sort of take advantage of some of these tools. So the type system wouldn't have helped us at all because it actually has the same type as it did before. However, if we were to give real names, and I've now added a name to the function, if we swap the function to now take %interest first and dollars second, and somebody tries to call the function with dollars first and %interest, their code is going to fail to compile. So what's cool about that is it means that here's how we do a refactor. We make the change that we want to change, and then we try and compile the code. It fails, we go find the first place that it failed, we fix that, we try and compile the code again. It fails somewhere else, we go fix that call site, try and compile the code again. And so if you've sort of diligently used types like this, refactors are super mechanical in Haskell. You make the change that you want to make sort of optimistically, you try and compile it, and then you go fix the compilation errors. And typically speaking, this is definitely not a rule, but you'll be surprised at how often your code just works when it compiles in Haskell. Definitely not guaranteed. Anyone who tells you that is wrong, but anecdotally, you'll be surprised how often it ends up being true, though, which is pretty cool. OK, let's see. Do we have time for the bonus material? Yes. OK. This is kind of along the same lines. We're going to talk about something called Boolean blindness and using types to fix it. OK, what does this mean? Does it mean Reid is a vegetarian, true or false? Does it mean that I'm old enough to vote? We have no idea, right? True doesn't mean anything. It's just an alternative with false. And even in Haskell, we're kind of often tempted to write functions like this. So this function is sort of a simplified thing that's saying, in Illinois, you have to be 16 to get your driver's license. Let's say in Michigan, I have no idea, you have to be 17 perhaps. So depending on the state laws, you sort of pass in a particular state and an age, and it tells you whether a teenager is old enough to sort of take their driver's license test. OK, so we've written this in Haskell, and we've been good. We did not use a string for the state. We didn't use an integer for the age. But we're kind of lacking in this one place, because when sort of like outside of this function, and we've given this function a name that's not at all ambiguous, or at least I think it's pretty clear, that if this function returns true, it means you can sort of apply to get your license. If it returns false, you can't. If we're unlucky, we've named the function in a way that you're not actually sure whether it's sort of written in a positive or negative way. Does false mean you can get your license, or does, right? If this is sort of worded at all ambiguously, you don't really it's not clear what true when calling this function means. And as soon as you've sort of left this tree of the program, you've lost the meaning. It's only when you sort of see a Boolean returned and you have the name of the function in hand do you know that true means eligible to apply for license and false means ineligible. And recall how simple it was to define Booleans in Haskell. Well, we can just create sort of a binary, sort of meaning we just have two choices, type that means something for our domain in particular. So we can say license eligibility, you're either eligible or ineligible. And adjust our type And now we don't even have to sort of have any name about like positive or negative sort of truthiness in the name to know which one is true or false. We're just classifying a driver, and the resulting value from this is either eligible or ineligible. And at any other part of the program, 10 call frames away, if we see this value in a debugger, we know what it means. We know that, if I have some record type that's like person, they have a name, and then if they have a license eligibility field in there, I know what it means. Whereas if they have, here's an example. Let's say I have a person object, and I have a field called license, and it's true or false. Like, does that mean they have their license? Does it mean that they were eligible to get their license, and I didn't use a very good name inside the person object? But here, we're really clear about what the alternatives are. The alternatives have sort of the domain built into it. And this was, really simple to define. The one place that we kind of care about something actually being a Boolean is something like an if statement. So we're doing like if the person is sort of eligible to get their license, like go down this branch of code. And we can easily replicate that by just saying if this value equals eligible. Now we've kind of turned it into a Boolean at the very last second. We're only turning it into a Boolean for the sake of the if statement. The Boolean sort of never escapes that scope to sort of be divorced from its context or intended purpose. So yeah, this is certainly something that you're sort of encouraged to do in Haskell. Okay, so the summary. New types allow us to create new types based on but not equal to existing types. We get to have as much or as little of the functionality from the existing type as we want, which is cool because it means we don't have to write a bunch of boilerplate code. It's also cool because if for some reason we don't want to be able to sort of take all of the functionality, we can sort of just take it piecemeal and actually leave out functionality, if that makes sense. And by using modules, we can sort of expose specific functions that sort of govern how our types are created, instead of allowing the user to sort of just create this specialized type based on its underlying representation. So we can sort of encode our business logic, and then in functions that take this sort of validated type or cryptographically signed type or sanitized type, we can be guaranteed that the only way that they could have created it is by calling the functions that we export from the module. So yeah, hopefully this has shown you some relatively, this is all stuff you would kind of learn, or mostly stuff you would learn in your first week of using Haskell. This is not using any fancy extensions, but for sort of day-to-day business logic type programming, I found that this is incredibly useful for sort of just instilling safety in my programs, that as they grow, I don't sort of get confused about what this parameter to a function means. It's a string, but does it represent the state name? Is it the initials of the state, like MD, or is it Maryland spelled out? Is it lowercase or is it uppercase? This allows you to sort of, in a really easy way, so you're encouraged to do it, take just a little bit of time and create more domain-specific types for your problem. Yeah, that's all I have. Happy to take questions and happy to sort of mingle afterward and answer questions in a smaller group as well. So thank you.